Well, as we continue our discussion about parametric curves or parametric equations, we're going to discuss the length of a parametric curve called arc length. I've drawn a diagram you can see, and for instance, suppose we wanted to know the length of that curve from A to B. Now, this curve is defined as a parametric curve, so we have a parameter, and I'm going to call it t in this case. Just in general, we'll say that this is defined by x, which is a function of t, and defined by y as well, a function of a function of t. We'll call it g of t. So here are our parametric equations. The parameter, of course, like I said, is t. Now that means that associated with this beginning point, we have some parameter value. And so I'm going to call that parameter value t subscript a. So it's the value of our parameter at that point a. And likewise here, I'm going to call the value of the parameter that gives us this point b, t subscript b. Now the general idea behind what we're going to do is we're going to cut that curve up into an infinite number of infinitely small pieces. And we can calculate the length of each small piece, and so we're going to use integration to add up the infinite number of infinitely small lengths, or that is, the lengths of each of those. So let's just take an example. Let's suppose we're going to take this infinitely small length. Obviously, I can't draw it infinitely small, but the length between those 2 points, that distance between those 2 points. And so if I called that distance, because it's infinitely small, if I called that distance ds, then the length that we're interested in, let's kind of get this in mind, the arc length, okay, of the total, okay? So the arc length is the length of the curve from A to B. From A to B. Now, so generally then, what we're going to do is we're going to take that one infinitely small length, but we've got an infinite number of those, and so we're going to add all those together. And we're going to start those infinitely small lengths at the point A, and we're going to go to the point B. So in the generality of things, that's how we're going to calculate the length of the curve. You know, where ds is the length of one infinitely small segment. Of the curve. Well, of course, that's not much to work with, so we need to do a little algebra magic, if you will, to be able to get to something we can deal with. So let's take where that we are on that curve. Let's magnify, if you will, this infinitely small piece. So let me see if I can kind of get us an idea here. It looks about like that where we are. Okay. And like I said, I'm going to magnify it so I have something to work with. And so this is that ds. Now, if we're infinitely small, then that ds actually approaches, if the interval is infinitely small, that ds actually approaches a straight line. And so because this is infinitely small, we're going to say that it is close enough in approximation to that straight line. So that straight line segment is what I'm going to call ds. I'm going to make the length of the curve in that straight line segment virtually the same because we're infinitely short there. Now, here's the rest of the story. If I drop a vertical and create a horizontal, we have a right triangle where ds is the hypotenuse. And remember, ds is infinitely small in length. This vertical distance, that is the leg that is vertical on this right triangle, is measured in the y direction. And because ds is infinitely small, that length is infinitely small. And the way we've done that in the past is we've called an infinitely small y distance dy. And likewise, the leg that is horizontal is measured in the direction of x, and it also has to be infinitely small. So we'll call that infinitely small leg dx, the measurement of that leg. Well, because of that, then we could write that because we have a right triangle where ds is the hypotenuse, we know that the square of the hypotenuse is equal to the sum of the square of the legs. But that means that ds is actually the square root of the sum of the square of the legs. So that's what ds is equal to. Now, with a little bit of, again, algebra magic here, we can create this, we can introduce the variable t. Okay, we can introduce the variable t. And by the way, to move along that curve ds, okay, that line segment, we have infinitely small pieces of time, okay, or of the parameter, of the parameter in this case. And so the measurement to go from the beginning point of ds to the ending point of ds takes a parameter change of time, infinitely small dt. So I'm going to introduce dt. And simply I'm going to do it in this way. Now dt represents something that's positive. It's a positive change here. I'm going to at least make that assumption. And here's what I'm going to do. I'm going to multiply this square root by dt over dt. So I haven't changed it. But the next thing I'm going to do is I'm going to take that dt that is in the denominator it's a dy squared there. And I'm going to write that as the square root of dt squared. So I still have dt over dt. Now furthermore, I have a square root times a square root. So this really ends up being, so I'm trying to conserve space when I probably shouldn't. That ends up being a dx squared plus a dy squared under the radical, and also a dt squared in the denominator, and a dt outside here. I just multiplied those two radicals together. Okay, we should be familiar with that. Now, if I look underneath the radical, I can break that into two fractions. Dx squared over dt squared plus dy squared over dt squared. I guess I'll do that. So now I have ds is equal to dx squared over dt squared plus dy squared outside the radical. Now, when I take one further look at that, then I could write that first fraction as dx divided by dt squared. And that second fraction I could write as dy divided by dt squared. And of course the dt outside the radical. Whoops. I'm sure you caught my mistake there. That's ds. So here's what we have then. The arc length of the entire curve, remember, the arc length of the entire curve, we were going to add up all of the tiny arc lengths starting at A and going to B, and each of those tiny arc lengths is ds. Well, we've just found out that ds is equal to the integral that the radical that we've got there times dt. So this is the same as the integral of the square root of dx divided by dt squared plus dy divided by dt squared dt. But now, this variable is all in terms of t. And starting at the point A has the parameter value t subscript a. So this is a t value that we're starting at, and we're going to the t value t subscript b. Now, of course, I'm sure I don't have to tell you the significance here is dx over dt is just the derivative of x with respect to t. And we ought to be able to calculate that. And dy over dt is just the derivative of y with respect to t. And we ought to be able to calculate that. And so this actually gives us that arc length that we were talking about previously. We have a formula for it now that is in terms of the parameter. In this case, the parameter is called t. Now, we could write that, okay, that's the arc length from, of course, t subscript a to t subscript b. Or we could say from point A to point B. Now, we might notice one other thing. If x, remember what we said up above, x is f of t. It's some function of t. And y is g of t. So we could write this a little bit differently. That is, we could say L is equal to the integral from our beginning t value, t subscript a, to our ending t value, t subscript b, of the square root of, instead of saying derivative of x with respect to t, we could call that f prime of t. Of course, that's squared. And instead of saying derivative of y with respect to t, we could call that g prime of t. And of course, that's also squared with respect to t. So we have a way now of calculating arc length when we have our curve defined as a parametric curve. But we'll look at an example on the next page. Well, here's our first problem. Find the length of the parametric curve defined by x equal 2 cosine cubed t, y equal 2 sine cubed t, and t between 0 and pi over 2, inclusive. So the way we calculate an arc length, of course, is it's an integral from our beginning parameter value, the t in this case, to our ending parameter value, b in this case, t subscript b, pardon me, the square root of, we're taking the integral of the square root, and under the radical we have the derivative of x with respect to our parameter, which is t in this case, that quantity squared, plus the derivative of y with respect to our parameter, which is, of course, t squared. And we're doing that with respect to t. That's the way we set it up. Now, I happen to get out my calculator and make a little sketch of this. And it's not really necessary for us to do the problem, but it's also kind of nice to know occasionally. So here's what I got. By the way, just kind of reminding you that if t is equal to 0, then the x value is 1, isn't it? I mean 2, pardon me. If t is equal to 0, cosine of 0 is 1, and when we cube that we get 1, and so x is 2 times 1, and so we have an x value of 1. Excuse me, 2 times 1 is 2, pardon me. So we have an x value of 2. At the same time, though, when t is 0, sine of 0 is 0. When we cube that, we get 0. So y is 2 times 0, so y is 0. So we'll say here is 1, here is 2 for the x value, so we're at this point. That's when t is 0. When t is pi over 2, we can real quickly say, well, okay, the cosine of pi over 2 is obviously 0. When we cube that, we get 0, so x is 2 times 0, or x is 0. In a very similar way, we'd find out y is 2. And so we're at this point. And then the curve looks something like this. That's what it looks like. So we're finding the length of that curve. Now, kind of built into our problem, it tells us the limits of integration because it tells us this curve is just defined from 0 to pi over 2 for their t values. So it's automatically telling us our t value is 0 beginning and our t value is pi over 2 ending. So that's not a problem at all. Now, we create a square root here, but to do this square root, let's come over here to the side because we've got a little bit of an issue going on. We need the derivative of x with respect to t. And when we look above, x is 2 times cosine cubed t. Well, when we take the derivative of cosine to the third power, we bring, let's see, what do? We bring that exponent down. 3 times 2 is 6, and we reduce the power on cosine by 1. But now we have to take, using the chain rule, have to take the derivative of cosine of t, which is negative sine t, isn't it? Well, so that means under this radical, this is probably going to be kind of long and messy here. Under this radical, we're going to have, in this derivative of x with respect to t, is actually negative 6. That's the 6 and the negative 1 with sine of t. Negative 6 cosine squared t sine of t, and of course that derivative is squared. Well, I'm going to run out of space, it looks like. Now, on the other hand, the derivative of y with respect to t, as we look above, y is 2 times sine cubed t. Well, that's sine of t all being cubed, so we would have a power on sine of 3, so when we take the derivative, we'll write that exponent 3 times 2, which is 6. We've reduced the power on sine by 1, so now we have sine squared. But we're using the chain rule, we have to multiply with the derivative of sine of t, which is just cosine of t. So here we have, and I'm kind of squeezing this in, we have the derivative of y with respect to t squared. And well, that is a derivative of y with respect to t is a 6 sine squared t cosine t, and of course that's squared, and I'm sorry, we've got that with respect to t. So I've really bungled that up and made a big mess of it there, haven't I? Well, let me drop down here because I've got all that stuff in there that is too confining. We've got to worry about this integral from 0 to pi over 2. Of course, that's really from the point 2 comma 0 to the point 0 comma 2. That's really, this is where t is equal to 0, and this is where t is equal to pi over 2. Okay. Well, if we do the squaring that we have under this radical, when we square that first term, we get a positive 36, negative 6 squared. We'll have a cosine to the fourth t, and we'll have a sine squared t. Plus, when we square the second expression, we'll have a 36 again, 6 squared. This time we'll have sine to the fourth t because we're squaring sine squared. And we'll have a cosine squared t. And of course this is all with respect to t. Now as I look further, this is going to be the challenge each time, is actually doing the integrals. Setting up the integrals is really straightforward. We're going to have to be a little clever here, and I'm noticing that 36 is a common factor under that radical. Are there any other common factors? 36 is a common factor. In the first term, I have a factor of sine squared, don't I? And in the second term, I have a factor of sine to the fourth. So sine squared t is a common factor. And in the first term, I have a cosine to the fourth. And in the second term, I have a cosine squared. So cosine squared is a common factor. And so when I factor those out, then what I'm going to have left over, when I factor out a 36 sine squared cosine squared from the first term, I'll be left with only a cosine squared t. And when I factor that out from the second term, I believe I'll have only a sine squared t, yes. And I'm integrating with respect to t. Well, of course, the significance is cosine squared t plus sine squared t is just 1, isn't it? So this becomes the integral from 0 to pi over 2 of simply the square root of 36 sine squared t times cosine squared t with respect to t. And we have to be real careful here because it's our tendency, I recognize, in generalities, it's our tendency to say the square root of x squared is x. But that's not true unless x is positive. I mean, remember, if we have the square root of 3 squared, of course that's 3. But if we have the square root of a negative 3 being squared, that's also 3. That's not negative 3. So we can't say that the square root of something squared is equal to what we're squaring. Generally, it's only true if what we're squaring is positive. What we can say is the square root of x squared is always the absolute value of whatever x is. We can say that. But that's a little bit difficult to deal with. So what I'm going to suggest when we look at this integral, remember our t values are between 0 and pi over 2. And for those t values, sine is always positive. Sine of t is positive for any of those t values. Now, what are we talking about? We're talking about this first quadrant, aren't we? And so for any t values in there, if you will, then the sine is going to be positive, and so is the cosine. So under the circumstances here, we have a square root of 36 sine squared t, cosine squared t, and we know sine is positive and cosine is positive because of the t values we're working on. So we can actually very readily say under those circumstances the square root ends up being a 6 sine of t cosine of t dt. Now we have something that's a little easier for us to work with. Clearly, we can factor out the 6. So we have the integral of sine of t cosine of t dt. And we could do a very simple substitution. We could say, let's let sine of t represent u. Then if that's the case, du, that is the derivative of u, the derivative sine of t, would be cosine t. So du is cosine t dt. So this is nothing more than du. Well, the integral of u du is just u squared, isn't it? So this ends up being 6 times u squared, but u squared is sine, is the integral of u, is not u squared, it's 1/2 u squared, isn't it? The integral of u with respect to u is 1/2 u squared. So we have 1/2 sine squared t. And we're evaluating that from 0 to pi over 2. Well, probably what I would also do is factor out that 1/2. Okay, I'd factor that out. And so I have 6 times 1/2, which is, of course, just 3. And so now all I'm having to worry about is evaluating sine squared t from 0 to pi over 2. Well, that's easy enough. That would be the sine squared of pi over 2 minus sine squared of 0. Well, we've got our 3 factor. Since sine of pi over 2 is 1, we have nothing more than 1 squared in that first position. And since sine of 0 is 0, we have nothing more than 0 squared in that second position. So we have 3 times 1. So the result here is 3. The length of that curve is 3. In this next example, as you can read, we're to find the length of the curve given by x equal 4t, y equal t squared, for t between 0 and 2. So what we know we're going to need, remember we calculate the length by integrating from the first t value, and here the first t value is 0, to the second t value, which is 2. We integrate the square root of the derivative of x with respect to t squared plus the derivative of y with respect to t squared, and we're integrating with respect to t. So to set this up, of course, we need the derivative of x with respect to t, and we need to square that. So as we set this up here, we have the integral from 0 to 2 of a square root. Well, the derivative of x with respect to t is just 4. So here we have a 4 squared. And the derivative of y with respect to t is 2t. So here we have a 2t squared. And we're integrating with respect to t. So as we calculate that, let's see, that's the integral of 16 plus 4t squared with respect to t. Well, certainly we can simplify that a bit. Okay, we can do a little bit of substitution. I'm thinking here that there's a common factor of 4, and we can take the square root of 4, so this is the integral from 0 to 2 of 2 times the square root of 4 plus t squared. all I did was write that as 4 times 4 plus t squared, and the square root of 4 being 2. And so we can factor out the 2, of course. Well, now we've got another issue here, don't we? If you'll notice, let's come up here for our scratch work, if you will. If you notice, we have a form that begs to use trig substitution. Okay, and if we're going to use trig substitution, because we have a square plus a square under a radical, what we need to do is use the substitution. We're going to replace t, in this case, with 2 times tangent of theta. And because when we do that, then what we have under the radical is 4 plus 4 tangent squared theta. Say that 4 plus t squared turns into that, doesn't it? And in that case, we can factor out a 4, and tangent squared, 1 plus tangent squared theta is the same thing as secant squared theta. So if we make this substitution, then our integral becomes the integral from 0 to 2. Now those are t values. Let's make sure we keep that in mind. Okay, of the square root of 4 secant squared theta. But we still have to worry about replacing dt, okay? And so we come back up here to where we started, and since t is equal to 2 tangent of theta, then the derivative of t with respect to theta, of course, is 2 times secant squared theta. And so dt is 2 secant squared theta d theta. So that means this dt can be replaced with 2 times secant squared theta d theta. Well, let's look at everything that's going on. We have the 2 factor in front, and we have t values here. We have to be careful of that. And the square root of 4 secant squared theta, we've seen in the past that we can make the assumption that secant of theta is positive, because that's the relationship we're going to use here doing what we've done. We saw that when we were doing trig substitution. So here we get a 2 times secant of theta when we take that square root, times a 2 times secant squared of theta d theta. Okay, and let's see, we can factor all those 2's out. We'll have the 8 times the integral from t equals 0 to t equal 2 of secant cubed theta d theta. Now, here's the next problem. To do this integration, this requires integration by parts. Remember when we did integration by parts, we saw this. This requires integration by parts in a special way, okay? We have to integrate twice, integration by parts twice, and then we have to combine the integrals. We did that a long time ago. So as I suggested at that time, this is one we need to remember. So, and I'll tell you what we get when we integrate this. We get 1/2 times the secant of theta times the tangent of theta, plus the natural log of the absolute value of the secant of theta plus the tangent of theta. Oops, except there's a 1/2 in front of that, my bad. Okay, so that's the result of the integration of secant cubed theta d theta. Now we're evaluating from t equals 0 to t equal 2. I suppose we could convert those to thetas, but let's finish the idea of how we integrate by trig substitution. Okay, so remember what we normally do is we set up our representative right triangle, and this is that angle theta that we're talking about. Now from above, since we have t is equal to 2 tangent of theta, if we solve for tangent of theta, we end up with tangent of theta is t divided by 2. And tangent of theta in a triangle, right triangle, this is a right triangle, is opposite divided by adjacent. So we could say this side is t and this side is 2. Now we have two sides of a right triangle, and if we solve for the hypotenuse, the hypotenuse squared will be 2 squared plus t squared, or 4 plus t squared. If we solve for that hypotenuse, using the Pythagorean theorem, we'll get the square root of 4 plus t squared. That's going to be that hypotenuse side. So what do we need below? We need the secant of theta. We already know that tangent of theta is x over 2. We need the secant of theta. Well, the secant of theta, okay, it's the 1 over cosine, so it's the reciprocal of cosine, and cosine is adjacent over hypotenuse, so secant of theta is hypotenuse over adjacent. So it's the square root of 4 plus t squared divided by the adjacent side 2. So now we have a way of replacing secant of theta and tangent of theta. Tangent of theta is t over 2. Secant of theta is the square root of 4 plus t squared over 2. Now, before we get very far, let's notice that we have a common factor of 2 with these two terms. Let's factor that out. So when we factor that when we factor that out, we have 8 times 1/2 or a 4. And so in here, we're going to replace secant of theta with the square root of 4 plus t squared divided by 2 times the tangent of theta, which is t over 2, plus the natural log of the absolute value of the secant of theta. And the secant of theta is the square root of 4 plus t squared divided by 2. And add to that the tangent of theta, which is t divided by 2, close the absolute value, and then we're going to evaluate that from t equals 0 to t equal 2. Well, we can certainly make things a little better by, we could simplify it, but let's just go straight through to the substitution. So we're first going to put a value of 2 in for t. And when we do, we'll end up with the square root of 4 plus t squared, which is 2 squared, okay? And so we'll end up with the square root of, 8 divided by 2 times 2 over 2, of course, which is just 1, plus the natural log of the absolute value. Well, we have the square root of 8 over 2 again, plus 2 over 2 again, okay? Now that's what we get when we substitute a 2 in for t. When we substitute a 0 in for t, we end up with the square root of 4 over 2 times the 0 over 2, plus the natural log of the absolute value of the square root of 4 over 2, plus 0 over 2. Now, I'm running out of room, so I'm going to compress a bit. Here's our 4. Of course, the square root of 8 is 2 times the square root of 2. So this ends up being the square root of 2 times the 2 we've got next to it, so we have 2 square roots of 2. Plus the natural log of the absolute value. Well, of course, this is a 1, and this is a square root of 2 right here. Okay, that's the square root of 2 when we simplify it. So we have natural log of the square root of 2, absolute value of square root of 2 here. Okay. And what we're subtracting over here, this is a 0, and what we have here really, square root of 4 is 2, so this is really the natural log of absolute value of 1. And of course, that's just natural log of 1, and natural log of 1 is also 0, so all that's 0. So this is all we've got left here. Now, we clearly could write that a little differently. And I suppose what we'll have here. Whoops! I see I've made a mess of this. Let me come back up to this line right here. Okay, what happens when I start running out of room? Remember, t was 2, and so in this position right here, we actually have t over 2. That's 2 over 2. So that's actually a 1 right there, isn't it? And I failed to put the 1 in that I've got here. So let me scratch this out. We have the 4, okay, scratching this out. What we have is the 4 outside the brackets, and the square root of 8 over 2 simplifies to just the square root of 2. And I'm sure you can figure that out. And then we have plus the natural log of, well, what is that? That's the square root of 2, the square root of 8 over 2, which is simply the square root of 2 again. Okay, so we have the square root of 2 here plus 1 here, absolute value. And remember, the rest of what we had, we were subtracting 0. So this is 4 root 2 plus 4 natural log of, and square root of 2 plus 1 is positive, so I don't need the absolute value, do I? And that's approximately equal to, well, I'm sorry, there's the exact value. There's the exact value. That's approximately equal to, if I get my calculator out, it's approximately equal to 9.1823. I mean, we're looking for the length of that curve, and so it's pretty important for us to have some number that we really know, roughly know the value of. Now, so the issue here is, as we found out when we were dealing with functions of x, like y is equal to f of x, way back when we were dealing with those, we can take something that looks fairly simple, and the integration, when we're doing arc lengths, and the integration itself takes quite a bit of work, because we really had to do two things here. We really had to use Trig substitution on the one hand, and then we got to a point where we're integrating secant cubed, and so that really required integration by parts, and I just reminded you of what that value was. Now, let's do one thing before we leave this problem. What did we actually do? We just solved a parametric set of parametric equations here, but if we take x, which is 4t, and we solve it for t, then we get t is x divided by 4. And what I'm doing is I'm eliminating the parameter. And now if I put that t value in the y equation, where we have y is equal to t squared, then this becomes y is equal to x squared over 16, or I'll write it as 1/16 times x squared. So we're really dealing with a parabola here, aren't we? Now, let's just a real quick sketch, okay, a real quick sketch. And that 1/16 is going to make the parabola rather fat, if you will. When t is 0, x and y are both 0. So when t is 0, we're at this position. But when t is 2, x is 8, and y is 4, isn't it? When t is 2, x is 8, and y is 2 squared or 4. So we'll say this is where 8 is, and we'll say this is where 4 is, just to get some rough idea. And so we're talking about a parabola, and this is the part of the parabola we're finding the length of that part of the curve. So, you know, finding the length of a parabola a long time ago, or parts of a parabola, we found out was difficult. But here we found out that we could do it, not easy, but we could still do it. Well, next with parametric equations, I want to discuss calculating surfaces that are created by revolving. They're called surfaces of revolution, surface areas of revolution. We'll calculate the area of a surface that's created by revolving a parametric curve about either the x-axis or the y-axis.